Hello, programming languages students. Welcome back for our final grammars video. In this video, we are going to talk about parse trees, and so what they are, what they do, why they're useful to us. And so first of all, let's just describe what they are. Parse trees are an ordered tree in which the root, or the starting rule, is the start symbol. Nodes are the left-hand sides of rules, so variables. And then children of a node are substitutions for the node. So basically you draw out a series of substitutions, and then you end in what are called leaves, which are the terminal characters. Then when you read the leaves from left to right, you get the yield of the tree, which is a sentence or a word in the language. So let's see our first parse tree here. We're going to work this for the grammar rules, where capital S goes to lowercase a capital S, or a capital A. Capital A, so the A rule goes to a lowercase b and back to the S rule or to a lowercase b. What this ultimately lets you produce is any string of A's and B's that ends in the letter B, and that's basically it. So if you follow a couple examples here and look at, man, if that's true, how could I produce AAA BA, right? You can go look it up, or AAA BBBBA. You can look it up. There's ways to produce it here, as long as it ends with a B, which I guess a couple of my little examples there did not. But hopefully, if you walk through a few of these, you'll see that it has to end in a B because this is the only terminal character here. But that's basically it. So it's any string of A's and B's that can end in a B. So if I ask you to draw a parse tree for something, I'll tell you what thing I want to produce, and you would have to draw out basically the substitutions or decisions you would need to make to produce that string. So in this case, we want to produce AABAB. So to produce our first A, we have to substitute S with lowercase a s. That way we can produce an A as our first character. Then we need to do the same substitution again to produce our second A. Next, we're going to need a B, so we substitute S with our A rule, and from our A rule we grab a lowercase b and go back up to our S rule. So then we need to substitute our S rule with another A, so we get S goes to lowercase a and another S, so we've produced AABA. And then from there, we take our last capital S, we substitute for A. And from A, we substitute for just the lowercase terminal b here. And if we read this left to right, we get AABAB. So figuring out this list of substitutions and rules, you'll get better as you practice a little bit. But that is the general gist. This is basically just drawing out the path that you need in order to produce a specific output. Let's do one more example together, and then we'll let you take a chance or try an example on your own. So we have a new language here. We have S goes to lowercase a, capital B, so a lowercase a terminal symbol, followed by an A rule and a B rule. A adds two lowercase b's in, and then loops us back to B. B can loop us back to A or put in lambda. So what this language ultimately is, by the way, is a series of strings, or any string composed of A's and B's that starts with an A and is followed by an exactly even number of B's. So 2, 4, 6, 8, 10, 12. And so hopefully by following through on this rule, you'd be able to see how that all works. So let's show the parse tree for A, B, 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 B. A, B, 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 B. A, B, 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 B. Or an A followed by 4 B's. And let's see what that looks like. So we start with our S. We only have one choice, so one series of substitutions. A lowercase a, then an A, then a B. And notice that the order matters here. I can't flip the order. It has to match the rule order. So from there, let's follow our A down. From our A rule, we only have one choice, lowercase b, capital B, lowercase b. So all three of those appear. Our lowercase b's are present here, but they're done. So we now have a capital B here, which we're going to loop back up to A so that we can add 2 more B's to our string. And then from there, we need to make sure we terminate all of our capital B's to make sure we have a terminal symbol at each spot. So capital B becomes lambda, and over here, we'd also need to go back and make capital B go to lambda. So now that we've done this, we have produced the string going left to right, A, B, B, lambda, which is nothing, B, B, lambda, which is nothing. So A, B, 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 A and 4 B's. We could have produced it a different way, by the way. We could have taken this B to go to A and then produced some B's over here and gone back to B and lambda and left this just as lambda. There are actually a couple ways to produce this string with this parse tree, which is a problem that we'll talk about a little bit later. But that's basically it. So another little parse tree example here. And so let me give you guys a chance to solve one. We're going to go back to a grammar that we wrote previously. And so this is one that we talked about, which is any string with exactly 2 A's. And so what I want to do is have you show me the parse tree for 3 B's followed by our 2 A's followed by a B. So why don't I give you a chance to draw it out? You can draw it on paper. You can try using writing it in PowerPoint like I did, or whatever works for you. Please feel free. So let me give you a few seconds to pause the video so you can try a solution on your own. All right. Well, assuming that you have produced your solution, hopefully it looks exactly like this. So our first substitution is very clear. We have to follow one specific pattern, capital B, capital A, capital B, capital A, capital B. From there, we have, from our B decision, we start with 3 B's. And so we have to draw all of our little B symbols here. Note that this last capital B ends in lambda, and you should draw it out, but I did not. So I will fix the slides with one little detail that I missed here. This should be a lambda. But we make the substitute for lowercase b, capital B, lowercase b, capital B, lowercase b, capital B. Then we get our A, which is our only substitution possible. Between the A's, there are no B's, so we immediately choose lambda. Then we add our other A in, and then we make one substitution for our B, and then go to lambda on the other side. So we get 3 B's, 2 A's, 1 B. So this is it. This is how you draw parse trees. It's just following rules and getting substitutions. Doing this can help for a couple reasons. One, it can make sure it helps you understand how the language works. By diving in through a couple parse trees, you get a much better sense for what's possible with the language and what's not possible. But secondly, it's also a good thing for proofs. So the last real problem with grammars, the danger zone if you're trying to create a grammar for a programming language, is one important thing. Programming computers cannot handle ambiguity. And so this ambiguity concept ties great into parse trees because you can use them to prove ambiguity. So ambiguity means 2 different ways to produce the same result in terms of grammars. So there's potential 2 different ways to produce one string, or 2 or more ways to produce one specific string in a language. And in programming, this is very bad. We should only have one real thing, one real path to a good sentence. And so what I want to talk about for ambiguity is that for any string in a context-free language, if there is more than one derivation tree that produces that string, then the language is ambiguous. That is very bad for programming languages. Ambiguity is not good. So if anybody proves that a programming language is ambiguous, then it's not a real programming language because it can mean 2 different things. So if this is the case, you can try to find equivalent grammars. There's multiple ways to write a grammar to produce a certain string, right? You could write a few different types of grammars to produce A, B, A, B, A, B. Depending on how you write it, some of those might be ambiguous and some might not. And so just because you find one ambiguous way to make a word doesn't mean it's impossible to make a grammar to create that word in an unambiguous way. It can't always be done, but sometimes it can. But we're not going to worry about that too much in this class. That's a really difficult problem that requires a lot of experience. What I do want you to do is be able to prove that a language is ambiguous. Um, so um, rather than focus on these pieces, what I want you to be able to do is prove that language is ambiguous. And to do that, all you have to do is find a string that you can produce in two different ways. So real quickly, as one example before I let you go, in this language, in this string, we produce the string A followed by 4Bs. We could have produced it following this pattern here. We could have also produced it a little bit differently. Imagine that we cut off the tree below this transition point. So when we transition from capital B to capital A here, let's say this was actually a lambda. So maybe another way of saying this is let's switch at the end when we go from B to lambda, and when we go from B to A, let's say we switch. This B goes to lambda, this B goes to A. That A goes to lowercase b, capital B, lowercase b, and that B goes to lambda. So this whole chunk of the tree gets cut off and switched with the last leaf of the tree. You still produce the string A followed by 4Bs, but you've produced it in a different way by making different choices. And so when you're proving ambiguity, that's the idea. You draw one tree to produce a string, and then you make different choices and produce the same string. So give it a shot. There'll be some examples on the assignments for you to be able to do this. And let me know if you have questions. See you next time.